this evening it's a great pleasure to introduce Dr. Katherine Johnson. Katherine is an associate professor here at Scripps at the Institute for Geophysics and Planetary Physics. A little bit of background: she received her Bachelor of Science from University of Edinburgh and then came here to Scripps where she received her PhD. She subsequently did postdoctoral work at the Carnegie Institution of Washington and didn't like the East Coast too much, I imagine. Perhaps, I don't know. We see a lot of return visitors here to Scripps, and here she is again. She's now a faculty member here and associate professor, again in IGPP. Katherine has quite a laudable scientific record. She's the editor of has been the editor of several prominent geophysical journals. She's a wonderful undergraduate and graduate teacher, and she's really dedicated a lot of her work here at Scripps and elsewhere to education. Most notable among these is that Katherine, for 2 years, actually served as the Education and Outreach Coordinator, Director for a program called I'm going to get the acronym wrong, I know it is IRIS, but it's the Incorporated Research Institutions for Seismology. And that is one of the education and outreach programs in the earth sciences that is held up as a model for many others in the country, and she was one of the leaders in that. One of my favorite stories about Katherine also involves her dedication to public outreach, and that is her starring role beside Bill Nye, the Science Guy, in a Discovery Channel special about the 100 greatest discoveries of all time. And in that episode of the Discovery Channel, Katherine discussed the structure of the Earth and the origin of the Earth's core. Today, she is going to take us on an extraterrestrial journey and look at planetary interiors, not just that of the Earth, in her talk titled Exploring Planetary Interiors. So thank you and welcome, Katherine.
Thank you. Thank you, Cheryl, very much for that introduction. And as Cheryl said, today I'm going to talk about exploring planetary interiors, and I'm going to talk about how we actually explore the interior of planets with remotely sensed data, so spacecraft, and in fact surface observations, because when you're looking inside a planet, then a measurement on the planet's surface is a remotely sensed observation. And so I'll be talking a lot about some very sophisticated kinds of methods by which we can look into the interior of planets, and sometimes we also use less sophisticated methods. So I'm just going to put this piece of silly putty right here, this column of silly putty up here, and this big purple column that I hope everybody can see, and we'll come back to that a little later on. As you know, silly putty is a solid that we can mold a little bit, but it's basically a solid, and we'll come back and we'll talk about the silly putty a bit later on in order to try to understand the interior of planets better. And I thought I would point out that I saw today on Webster's dictionary the word explore, to travel to unknown territory for scientific purposes, which I thought was really the right phrasing for what we do in planetary science and what we do at Scripps for a lot of exploration of, for example, the Earth also. Okay, I'm going to focus today on what we call the terrestrial planets. These are the rocky planets of the inner solar system here, and shown not to scale. I'll talk a little bit about the Earth. It's the third planet, of course, from the Sun, as you know. And its nearest neighbors are Venus, closer to the Sun, Mars further away. And then also among the terrestrial planets is Mercury, the planet closest to the Sun. I won't talk too much about Mercury today. I will talk just a little bit about the Earth's moon. So we won't talk about the gas giants of the outer solar system here. This little sketch was done by somebody in our introductory planetary class earlier this year. But an important place actually occurs in the solar system between Mars and the gas giants, and that's known as the asteroid belt. It's a place where there are small, compared with planets, rocky bodies that are often hit the Earth, relatively often, as meteorites, and provide some information on what we think the earliest solar system material looked like, the earliest inner solar system material. And so we'll talk today a little bit about how we can explore the interiors of the terrestrial planets. And so to do that, we'll talk first just a little bit about the Earth, stuff that most of you will know already, that it's fun to remember and to put together as pieces of trying to understand a puzzle. And what I'm going to do today when I talk about the other planets, particularly Venus and Mars, is I'm not going to tell you one single story. What I'm going to try to show you is that as planetary scientists, what we try to do is we try to figure out little pieces of the jigsaw puzzle. And the piece that we figure out this week may be completely different from the piece that we're figuring out next week or next year. And when we figure them out, we may have absolutely no idea how they fit together. But then a large part of what we also try to do, if we're good scientists or trying to be good scientists, is to make sure that those pieces do eventually fit together. So what I'm going to tell you are some short sound bites, if you like, about some of the recent discoveries, some mine, many other people's, for Venus and Mars, and show you how we can sort of weave that into a story that helps us understand the interior of those planets. Okay, so first just to review a little bit about what we know about our own Earth. We know, of course, that it is different from anywhere else in the solar system. It has an atmosphere, nitrogen and oxygen, that is capable of supporting life and water, and this is one of our colleagues, Professor David Samwell at Scripps, enjoying the fact that Earth provides this unique environment. And the important thing to remember is that the atmosphere and the hydrosphere are coupled. They result in weather, they result in the water cycle as we know it, and over longer periods of time the exchange of water between the liquid part of the Earth and the solid ice part of the Earth is important when we look at, for example, ice ages. We also know many other things about our Earth. We know that our Earth revolves on its own axis with a time scale that is short compared with the time it takes to go around the Sun. 1 day, 24 hours on its own axis, 1 year, 365 and a quarter days around the Sun. We know, of course, because we live on the Earth, that we have seasons. That's due to the fact that the Earth's equator is not quite in the same plane as its orbit around the Sun, or in other words, its rotation axis is tilted so that here you would have summer in the northern hemisphere, and here at this place in its orbit you have winter in the northern hemisphere. We know today that that tilt is about 23 degrees, but that it's been different in the past, significantly different, and that's what gives rise on geological timescales to large-scale climate change. And we know, of course, being right by the ocean, that we experience tides on the Earth due to the Earth's gravitational interaction with the moon. And so the important thing is we'll come back at the end and see that the moon also experiences tides on it due to the pull of the Earth, for example. And so again, the important message to take away from this slide is that what we experience in our daily life on the surface of the Earth is the manifestation of many of these things that are coupled that we don't think about on a daily basis. The fact that the Earth spins on its axis, goes around the Sun, and experiences tides due to the moon. We know that the Earth's topography we know that we have continents and oceans on the Earth, and we know, thanks due to a lot of work done, in fact, at Scripps Institution of Oceanography from the 60s onwards, and more recently with satellites by David Samwell and colleagues, we know that the ocean floors, shown here in color, we know that the ocean floors are not completely flat. They have mountain ranges in them, ridges down the center of the oceans, we'll come back to this, where plates spread apart, and trenches around the edges where crust and lithosphere is subducted back into the Earth. We know that there are island chains in the oceans. These are the manifestations of moving plates, we'll come back to that, across warm spots in the mantle that allow melting and the production of volcanic islands. And an important thing to remember from this slide is that there are big differences between the average age of rocks that make up continents and the average age of rocks that make up the oceans. Some of the continental rocks are extremely old, back to 4 billion years old in some cases. But all oceanic rocks are much younger, 300 million years or less. So Ocean floor material is an order of magnitude younger than continental material. We know we experience earthquakes and volcanoes. We know about earthquakes here in Southern California, and we know about earthquakes from volcanoes from other places. And these, again, are the manifestation of not just something that happens on the surface, but they're surface expressions of the way in which the Earth is losing heat. So we might expect this perhaps to have happened or be happening on other terrestrial planets. And they affect the atmosphere through releasing gases and volatiles, for example, during volcanic eruptions. And the last sort of piece of information about the Earth that we know about and is relevant to our discussions today is that the Earth has a magnetic field. We've known this for a long time. The Chinese knew it many, many centuries ago, and we've used it for the purposes of navigation for hundreds of years. And what does that magnetic field look like? We know that the Earth essentially has a north pole and a south pole. Its field looks a bit like the field that would be produced if you were to put a big bar magnet in the center of the Earth and align it with the Earth's rotation axis. That's not how the field is generated. It's generated, in fact, by fluid motion of liquid iron in the Earth's outer core. So a conductor, metallic conductor, that can move and generate a magnetic field. And why is a magnetic field important? It's important because we can actually use it as a clue when we're trying to play detective in terms of understanding the geological history of the Earth or perhaps another planet, because the Earth's magnetic field is actually recorded in rocks, particularly in volcanic rocks. As they cool, they acquire a magnetization that represents the field at the place and time that the rock was extruded. And so you could see how you could build up a record of the Earth's field behavior at a particular place. For example, if you had a series of lava flows of different ages. The magnetic field is also important. It's very important to us, to our atmosphere. It protects our atmosphere from the solar wind, and also is important to the survival of life. So from all these things that I've just gone through very quickly, that would be the subject of at least one whole introductory course in earth science, we know that the interior of the Earth has several different layers. We know that the Earth has a metallic iron core, the innermost part of which is solid, the outermost part is liquid. And then the rest of the Earth is made up of silicate rock, kinds of rock that we find on the Earth's surface, and the mantle, that's the crust, and the mantle, which is made up of rock of similar composition but is more dense than crustal material. It has more iron and magnesium in it than crustal material. So there are compositional layers, and then of course one would put on top of this the atmosphere and the hydrosphere. And we know about these layers from many different avenues, but primarily because we can take samples at the surface, try to figure out how they got there and why, and we can figure out how energy travels through the Earth as it is released, after it's released by giant earthquakes. And so we can actually figure out the detailed internal structure of the Earth quite well because we have earthquakes and because we can measure them. And we also know about the liquid iron core because of the Earth's magnetic field. So it's important to bear in mind how we know those things when we come to look at other planets. And some of the things that I've talked about are not just the manifestations of these compositional layers, but they happen, for example, earthquakes and volcanoes, and in fact the Earth's magnetic field, happen because of how rocks and metals can behave. So it's not just what they're made of, but it's how they can behave, and not how they can just behave today or yesterday, but how they can behave on geological timescales. That's really important. And so to understand that, we come to our high-tech experiment here with the silly putty, and this is really just to try to give an understanding of how things that we typically think of as rocks, solid, might behave differently on geological timescales. So we all know that silly putty is more or less a solid. You don't open up the little eggshell can that it came in and it doesn't run away from you. You know it's a solid. You know if you pull it hard enough, it'll break. And you know that if you roll it into a really good ball, it'll bounce, and I won't, so it might go somewhere other than back to me. No, fortunately not. So it bounces. But we also know that if we leave it long enough, like our experiment that we started out with here, that it will flow. So we started out with a big purple pillar here, and now you'll see that this has flowed. Just in the time that I've been talking, the last 15 minutes, this has flowed out over the plate. And if we leave it there long enough, it will eventually cover the whole of that plate. So on a longer time scale, under the force of gravity, the silly putty has flowed. And so we've seen 3 different behaviors, and this turns out to be not a bad analogy for how rocks can behave. We've seen that the silly putty can break. If I apply a large stress over a very short time scale, it'll break. The same thing happens to rocks, except the stresses are enormous. And the time scales are long compared with the time scale of me breaking silly putty, but short geologically, so a few hundreds of thousands of years perhaps. It can bounce. If we apply smaller stresses over a shorter time scale, it can behave elastically. So it'll go back to the shape it was originally. And the Earth behaves like this. Most of the Earth behaves like this after a large earthquake. Where the earthquake happens, the rocks break, but the rest of the energy is propagated through the Earth by the Earth behaving elastically. It just deforms a little bit and goes back to its original state. But over longer time scales, with moderate stresses applied, something that we think is a solid can actually behave as a fluid. It can flow. So it's not a fluid in the way that we think of fluids typically, but over very long time scales it can flow. This turns out to be really important in the way that the Earth behaves because it relates to how the Earth and other planets can transport heat. So we've just talked about the compositional layers of the Earth. But we know as we go deep inside a planet, temperature increases and pressure increases because of the overburden of rocks. And there are 2 competing effects. Hotter rocks are weaker. So if you think of corn syrup, when it's hotter, it flows more easily. And rocks under higher pressure are stronger. So these things compete with each other as you go deeper into the Earth. And the same will be true of other planets. So this is actually a generic description, not just one of the Earth. On the Earth, of course, we have the exception that we have a liquid ocean. So then we have a different kind of layering in the Earth that is the one that is the most important for the Earth's geological history, how it's lost heat over time, and the same will be true of other planets. We have an outer layer that's cold. And this comprises the crust and the top part of the mantle, and it behaves rigidly over time. It supports stresses elastically. If the stresses are too big, it breaks. The rest of the mantle behaves very much like the silly putty on the plate here. Over long time scales, it flows. The outer core is liquid iron. In fact, it has the viscosity of water. Even though it's under tremendous pressures and temperatures, it's extraordinarily fluid. So it flows, but much more efficiently than the rest of the mantle. And the inner core is solid. So this is very important to how the Earth cools. And so we can think of how the Earth, or a generic terrestrial planet, might cool with a simple kitchen experiment. Here, you can think of this as being taffy in a pan. So you've heated it up from the bottom and it's melted and it's just convecting. So the fluid is moving around. It can transport heat very efficiently from the bottom to the top. Then you let this cool. You might cool it by blowing air on it from the top, or cool it by cooling it from the bottom. But we'll think about cooling it from the top here. The top will start to form a brittle layer, but the interior will still be molten. So this is still convecting, but the whole system can't lose heat as fast because of this brittle layer across heat, which heat will be transported by conduction. So this brittle layer actually inhibits the loss of heat here. And so we can actually take this analogy and look at a planet here. And so the bottom of this pan here would now be the boundary between our planet's mantle and the core. So heat is being supplied from the core to the mantle, and the planet is trying to lose heat by convection, something that is solid but warm and can move on long time scales. But then there's an outer, rigid, stagnant layer. And over time, this stagnant layer will thicken, and it inhibits the loss of heat from this mantle. One way that you can improve things from a planet's perspective is if you can break this lithosphere, and this is in fact what happens on the Earth. We have plate tectonics. If you can break this lithosphere and take it down into the mantle, this is cold material, and so you stir in. It would be like breaking this crust on here and stirring it in, and it helps you to actually cool the mantle. So it turns out that for the Earth, well, we have plate tectonics. We know that the Earth is made up of these major plates, that this assists the Earth in its cooling greatly. And the evidence for this are many of the things that I talked about earlier, in particular that most of the earthquakes and volcanoes on the Earth occur at plate boundaries, where new crust or lithosphere is formed and where lithosphere is destroyed. And so what we've seen that's going to be really important to looking at other planets is that there are a lot of connections on the Earth. This is the most important thing, perhaps, when you go to look at other planets, because you have less detailed information, and so you need to try to put those less detailed but varied types of information together. And we know that there are strong connections amongst almost any process that we could think of on the Earth. What's happening in its deep interior, what's happening on its surface, its atmosphere, and even how that relates to its motion in space. And we have a surface record of what's gone on over most of the history of the Earth, the last 4 billion years. And so the question is, are other terrestrial planets similar? How can we look at them? How can we construct their histories? And we'll start by looking at Venus, Earth's nearest neighbor. Before we do that, what I wanted to say here is that you can actually do quite a lot just from the Earth. So two really simple things to think about are, you read any textbook and it says Venus is this big and Venus weighs this much. Venus has this mass. Or Mars is this big and Mars has this mass. How do we know? How do we know how big a planet is? How do we know how heavy? How do we weigh a planet? And we can do a lot of those things from the Earth. We can determine its size optically with telescopes. We can weigh it, in quotes, by seeing how long it takes a satellite, natural or artificial, to go around that planet. That turns out to be related to the satellite's distance from the planet and the mass of the planet. So if a planet has a moon, you can figure out how heavy the planet is. You can figure out things like its average surface temperature, maybe the average temperature at the top of the atmosphere, by looking at radiation from the planet, and a little bit about composition. So you can do a lot without even leaving home, so to speak. And by doing that, we know that the other terrestrial planets are like the Earth in that they have mantles, shown here in yellow, and cores, shown here in gray, at least part of which is fluid in the case of Venus and Mars. Venus is approximately the same size as the Earth, and its core is approximately the same size as Earth's core. We don't know whether part of it is solid or not, part of its core is solid or not. Mars is about half the size of the Earth and correspondingly smaller core, and the Moon has a tiny little core. We also know that these other planets have crusts. We don't know that from Earth-based observations. I won't talk about how we do that, but the important point is that they're not terribly different in many ways from the Earth. The thing that is different about Venus and about Mars is their atmospheres, primarily carbon dioxide atmospheres. In the case of Venus, much thicker than that of the Earth. In the case of Mars, much thinner than that of the Earth. And so the question is, are any of these observations that we see on the Earth today, how do they compare with what we know about other planets? And so what I want to show you here is that we've learned a lot from some recent missions to Venus and to Mars. Venus is often referred to as the morning or the evening star. You see it low in the sky in the early morning or early evening. And it's also often referred to as a sister planet because of those similarities in size, mass, and density. However, if you look at Venus through a telescope or even from a satellite in the visible wavelength, this is what you see. Not really anything terribly interesting. You see the top of the cloud layer on Venus. And if you look at it in the ultraviolet, well, it looks the same, except you can color it purple if you like. So not terribly interesting. So we need to use different kinds of techniques. We need to use microwave imaging to be able to actually see through the clouds. And there's been a lot of exploration of Venus, primarily by the former Soviet Union, very successful in exploring Venus. In fact, the first landers on any other planet was a Soviet lander on Venus. This was before we landed on the moon, even, ever. So the first landers by the Soviet Union, and then various satellites in orbit around a planet. And landers and satellites give you different kinds of information. Landers, the Soviet landers, lasted about 40 minutes. The reason for this is the atmosphere of Venus is so thick that surface pressures are about 90 atmospheres. That's not too bad, 90 times that of the Earth. That's not too bad. The thing from an electronics perspective is that the surface temperature is 450 or so degrees centigrade. So it's not a nice environment in which to work. But we have some images of the surface, and we know from these landers about the composition of the atmosphere, the temperature at the surface, the pressure at the surface. So we know quite a lot from these landers that lasted in very short time in very specific places. And we know that the surface is essentially a volcanic kind of rock, again, similar to that of the Earth. But there are these huge differences in surface conditions because of the different atmosphere. We also know that Venus has essentially no magnetic field, and that it is dry. There's no water in the lower atmosphere or near the surface. The results that I'm going to talk about come from the Magellan mission to Venus. This was a United States mission, a NASA mission. The Magellan spacecraft was actually the first spacecraft to be launched from the space shuttle. The space shuttle has actually been important for planetary exploration because it's been a vehicle for launching many different spacecraft. This carried one instrument, a radar instrument, two antennas, so the radar goes alternately in time between these two antennas. This big one here points off to the side when the spacecraft is in orbit around Venus, and this smaller one here points directly down. The large one is used to form images, radar images, so not visible wavelength. And this one here is used to measure the travel time of a radar pulse from the satellite to the surface and back. So we know how high the satellite is above the surface, so you can measure the elevation of the surface of the planet. And then you can measure the planet's gravity field by detecting tiny variations in the acceleration of the spacecraft as it goes around the planet. So from this we have really nice map of the topography of Venus. So the important thing here is that in this figure, red is high elevation, blue is low elevation, and despite the fact that it looks from this image that about half of the figure is red and half is blue, you'll see that the color is stretched here. And so unlike on the Earth, where 60% of the Earth's elevation is at the average ocean floor depth and 40% is at the average continental height, on Venus almost all of the planet is within 1 kilometer of its mean elevation. That would be this green color in here. So no continents and oceans in terms of topography on Venus. It's dry, no water on the surface, and no global system in the topography like we see on the ocean basins on Earth of things that look like plate boundaries, ridges, trenches, or transform faults. However, Venus does have things that look like tectonic activity on the Earth, just not in an organized way of plate tectonics as on the Earth. So there are things that look, sorry, I forgot to put scales on these. This is about 20 kilometers across, so is this, and this is about 100 kilometers across. There are things that look like ridges and fractures in here. This is something that looks like a rift. If you look carefully, this is an impact crater here, and you will just see the outline of the very edge of it here. So it's been pulled apart by tectonic processes that have faulted the lithosphere. It has volcanic processes. Here's a massively exaggerated to the embarrassment of JPL at one point, a view of a volcano on Venus here. This is made by draping the radar image over the topography And you see an impact crater, for example, here. These are images of some other rather peculiar-looking volcanoes. This is a feature that I'll talk about a little bit more in a minute. It's a feature known as a corona on Venus. And there are impact craters on the surface, sometimes later flooded by lava flows in their center. And impact craters on other planets are extremely important to understanding the planet's history. One of the things that we know for the Earth is we know about time, because we're able to take rocks, measure their ages radiometrically in the laboratory. But when you go to another planet, you don't bring a sample back. Even if you bring a few samples back, they may not be representative. You need some other way of measuring time, and one of the ways in which we do that is to look at impact craters on those planets' surfaces. And so Venus is quite unusual. When you look at the moon, you've seen pictures of the moon, extremely heavily cratered. Those surfaces on the moon that are very heavily cratered date back to some of the earliest surfaces in the solar system history. Venus, by contrast, has no really heavily cratered areas anywhere on its surface. It has very few craters compared with what we might expect for a planet its size, and they're distributed more or less evenly over the surface. So there's no area that seems to be really old, that's been exposed to impacts for a long time, compared with a younger area. It all seems to have kind of the same age. And from the number of impact craters, we get an average age for that surface of about 750 million years, so less than a quarter of the age of the planet. And one of the things that ends up being very tricky in trying to understand Venus is that we don't know anything about regional age variations because of this low number of impact craters. And so one of the things that we know, but we don't understand well at all for Venus, is that at some time, approximately 750 million years, and there are big error bounds on this, years ago, it underwent a huge change where most of the surface was somehow resurfaced, had volcanic activity going on, resurfaced that surface, perhaps over 100 million years, 200 million years or so. And since then, there has been much less volcanic and tectonic activity. We don't know about current tectonic activity. We suspect it does have some, but we haven't sent seismometers there to figure that out for us. So the impact record for any planet, very important in understanding its history. These features called coronae that I mentioned before, these are very peculiar. We haven't seen these on any of the other terrestrial planets. They're things that are almost circular. They're not volcanoes, but they have volcanic-like structures in them. This one has little volcanoes in the center of it. They have a lot of volcanism associated with them and a lot of fracturing. They're circular. They're probably related to things that are like hotspots on Earth in the Venusian mantle, but probably different in terms of their dimension. And these have varied. If we were to look at not an image, but the topography, they're varied. Some are high, some are low. But mostly they have a rim here that's a high rim around them. And most are about 200 kilometers across. So these are not small features. And we can use them to actually try to understand more about the internal structure. So we can't use seismology yet for Venus to understand internal layering, but one of the ways that we can look at those mechanical layers that I talked about earlier is we can look at what happens to the surface of a planet when you put a load on it. And a load can be a volcano. In our case, it's going to be a corona. And when you load it, then that outer part, the lithosphere that we talked about that can behave elastically, will bend. If the load isn't too big, then it will bend and support that load by flexing, just like a ruler when you bend it at the end. And for a thinner plate, there'll be more flexure closer in to the load. And for a thicker plate, there'll be less flexure, and it will extend further away from the load. So it's a diagnostic, the response of how this topography responds, to this load tells us something about the thickness of the lithosphere. And so we can then go back to this slide that I showed earlier, where if we can use this to look at the thickness of the lithosphere, you can perhaps distinguish between a case where you have a thick lithosphere and an efficient cooling of the mantle, and a thinner lithosphere that might be consistent with plate tectonics, and where you can have more efficient cooling of the planet's mantle. And so we can actually do this for Venus. This is just an example. This is an elevation map. So red is high here, and blue is low. And you see this characteristic flexural signature here, where it will go from, as you go from the red high, it's going to go blue, and then a little bit higher as you go further out here. So it goes red high over to the blue, and then there's a flexural signature. And if you take profiles across that, it looks like a flexural signature here. And so you can model those and figure out how thick the lithosphere is that's supporting that. And that thickness is directly related to how much heat you can get out of the surface. And so you can do this. You have to do a lot of other things that I won't talk about here tonight to try to figure out how you add temporal information to this. But the bottom line is that when you do this for Venus, don't worry about the words. The lithosphere is thicker and consistent with much less efficient heat loss on Venus than on the Earth today. And this is entirely consistent with what we see in terms of geology, but it's a different way of getting at it. It says that we don't have any evidence from the thickness of the lithosphere to say that we have plate tectonics, and that's consistent with what we see in the geology. It's also an important tie. This is where, when I was talking about putting the pieces of a puzzle together, it's an important tie into understanding other things about Venus. Remember, I said in passing that Venus doesn't have a magnetic field. Well, one of the things that enables the Earth to have a magnetic field is that plate tectonics is very efficient in cooling the mantle, so you can lose heat efficiently from the core, and so the core, fluid in the core can be driven by that loss of heat and can actually make magnetic field because it can move easily. On Venus, the heat loss through the mantle is much less efficient, so the core can't cool as efficiently, and so you can't actually support a magnetic field. And so you can put these pieces together to try to understand the whole picture. And so then you come up with a series of things that show Venus as being a very different planet from the Earth. It might be Earth's sister planet, but it's certainly not an identical twin. It has a thick carbon dioxide atmosphere. Maybe this is related to this period of large amount of resurfacing, 750 plus or minus a few 100 million years ago. And we'll wait till that comes back. And as I said, it cools very slowly compared with the Earth. It cools slowly, less efficiently than the Earth, and can't support a magnetic field. We've seen that Venus is quite different from the Earth, although it's quite similar in its size and its mass. Mars is, at first glance, quite different from the Earth, and one might ask, is it similar to Venus? And so what I hope to show you, but we may not get the actual visuals that come with it, is that perhaps the most important bottom line for Mars is that for Mars, as you know, we've been exploring Mars over the last decade with satellites and with landers. There's been an enormous amount of exploration of Mars, and both in terms of just going to specific places on Mars and in terms of taking satellite observations that enable us to measure its topography, like for Venus, but in fact incredibly accurately for Mars. We know the height of places on Mars to within about 30 centimeters. That's phenomenal. And we have beautiful images from several different missions now. We have visible wavelength images. It's okay. It's just a planetary mantle. Don't worry about it. And so one of the most important things for Mars is that in contrast to Venus, where for Venus we've seen that we've learned all these things that show us that it's quite a different place from the Earth today. But the other really important thing about Venus is that we don't know anything about the first 3/4 of its history. So what happened in the first 3 billion years, that record is gone, and we don't have very good ways of figuring it out. For Mars, we turn out to have a quite different story. and I'll still leave this slide up here. Some of you may have gone to Balboa Park a couple of years ago for the close encounter with Mars, which happens about every 60,000 years or so. And so we've had much better views of Mars, this is just what I was saying, from these more recent missions. And the most important thing to take away from a picture of Mars is that it has two quite different hemispheres. It has a southern hemisphere here, so this is elevation on Mars. High elevations in the southern hemisphere, very heavily cratered, so you might think, aha, like the moon, an old surface, and that would be true. In the northern hemisphere, a much smoother surface, and so you might think a much younger surface. And in fact, this was believed to be true until some of the more recent missions, in particular Mars Global Surveyor. You also see this region that we've known about for a long time, the Tharsis region. That's this whole area here in the left-hand side of the figure, which encompasses Olympus Mons, the largest volcano in the solar system, and the three Tharsis Montes, large volcanoes on the Tharsis Rise, and major impact basins in the southern hemisphere. And so many of the things that we have learned over the past decade have completely changed our view of Mars. And so I'm just going to skip over some of these, but I'll point them out using this figure here. First of all, until more recent missions, we thought that essentially this was kind of a generic history of Mars. You make the crust in the southern hemisphere very early on in Mars's history, 4 billion years ago or so. And you make the crust in the northern hemisphere more recently. Then, even more recently than that, there was volcanism that led to these large volcanoes of the Tharsis Rise. And that order of timing comes from the relative decrease in impact craters on those surfaces. And we also saw in images from Viking days that there was evidence for water in Mars's ancient past, and it doesn't appear to have a present-day magnetic field. Again, no evidence for plate tectonics on Mars. And we've revised several of these conclusions with data from these new missions. The first one that we've revised is that the northern hemisphere on Mars is not actually young, it's quite old. And the way in which we've been able to do that is that craters that don't show up in images of the surface show up in the topography. They've been buried, and so a crater rim actually shows up in the topography, but not in an image. And so in the northern hemisphere, we're able to look at craters from the topography data and see that the northern hemisphere of Mars is at least as old as the southern hemisphere, but is just covered by maybe a mile or so of thin veneer of younger lava flows and sediments. And this is consistent, perhaps, with the directions that have been measured for valley networks on Mars. These are things that look like valley networks on the Earth that may have transported material from the southern hemisphere to the northern hemisphere to provide a smooth cover of older material in the northern hemisphere. Then, with data from the Mars Global Surveyor, Mars Odyssey, the European Mars Express mission, we have some beautiful images of the Tharsis volcanoes. We know that there are these three central volcanoes here, large Olympus Mons. You can see it in this figure here. This is bigger than Hawaii. It's basically the size of the state of Arizona. So it's that's a volcano. So it's enormous. And in fact, the crater at its top, the caldera at its top, for those of you who've been to the calderas on Hawaii, seen some calderas, this caldera goes from San Isidro at the border to San Clemente north of us. So it's enormous and thought to be young in terms of its surface. But in fact, from Mars Global Surveyor, we've learned something really quite extraordinary, which is that most of the Tharsis region is very old, is in fact 4 billion years or older. And we know this from exactly the same kind of method that I just talked to you about for Venus, for looking at Venus's lithosphere. If you take Mars and you sit a big, huge lump of volcanic material that's now this whole area on the top of it. So think about a beach ball and putting your hand into the side of the beach ball. Then the beach ball flexes around your fist. And the flexure of that surface we can actually see on Mars. And that surface will flex, and it will have stresses in it because it was flexed. And in fact, the stresses in that topography account for many of the directions of very ancient faults on Mars. So these faults that we know are very, very old are predicted, their directions are predicted by simply putting a big load, the size of Tharsis here, on Mars very early on in its history. And then, in addition to that, these valley networks flow downhill from the topography that results from that. So quite an elegant way of getting at the fact that Tharsis itself, which probably has formed over something like a hotspot on the Earth, except we have no moving plates, formed a long time ago. And volcanism has persisted in that one place for over 3.5 billion years, because we know that there are some surfaces that are geologically very young. And Tharsis was probably extraordinarily important in the same way that this resurfacing period on Venus was important to climate. The formation of Tharsis was probably very important to Mars's climate. Huge amounts of volatiles would have been released, and one of the areas of ongoing research in the planetary community is to try to figure out how much volatiles could have been released and when, and how you might actually keep them there. And one of the things that I won't talk about, I'll skip over here, we can talk about it in questions if people are interested, is that Mars does actually have a magnetic field. It has a magnetic field that is not due to fluid moving in its iron core, but it's a magnetic field that was recorded in very old rocks on the surface. So it's a magnetic field that happened a long time ago on Mars, probably right around the time that Tharsis was forming. And this may in fact tie in very importantly to the formation of Tharsis, to the formation of the northern and southern hemisphere crust on Mars, and to the ability of Mars to actually have a different climate from its present day climate, and perhaps have had water on its surface. And so it's very likely that crustal formation on Mars, its magnetic field, volcanism, its climate. So again, these links between the core, the surface, and the atmosphere, these links have been extremely important in understanding Mars. And so the last thing that I just want to allude to is to go back to something I said at the beginning. Some of the work that I'm doing right now with Renee Bulow at Scripps is in fact looking at tides, but not on the Earth, looking at tides on the Moon. And as I mentioned, the Moon exerts a gravitational pull on the Earth that causes tides that we know of in the ocean. It actually causes tides in the solid body of the Earth. It's just that we don't see those with our naked eye, because the solid body responds much less, or has much less deformation compared with the deformation that we see, with the tides that we see in the ocean. The same thing is true from the Moon's perspective. The Earth makes tides on the Moon, and so the Moon is alternately pulled a little bit towards and away from the Earth. And those stresses in the Moon actually result in moonquakes deep in the Moon, in fact much deeper in the Moon than any earthquakes that we see on the Earth. And one of the things that we've been looking at is some of the data that was collected by the Apollo astronauts. And the reason that I mention this right now is just so that you see that many of the things that we do in science don't just come out of the neatest, most interesting, most recent mission, but some of the things that we go about discovering, and this is actually, I think, some really exciting work that we're doing, and it comes out of a data set that is by current standards of poor quality, but is truly the only record that we have for that planet of that particular process. And so to go back to talking about the Earth and its place in space, we're trying to understand how the Earth affects the Moon. And so I'd like to leave it there and thank you all for coming, and sorry about the technical hitch in the middle. Thank you. So the question that the gentleman asked was, I talked about elasticity on Venus, and what is it that causes the loading of the lithosphere on Venus? It can be many things. Specifically here, I was referring to these large, almost circular features called coronae that are about 200 kilometers across, and they have high topography associated with them in many cases. Sometimes they may actually have some dense material underneath the surface that we can't see that's also pulling the surface down. So that sits as a load on the surface and causes the surface around it to deform. A volcano will do the same thing. We do actually see the same thing around some volcanoes on Venus, but it's harder to see because what happens when you have a volcano is, of course, it deforms the surface, but then eruptions can fill in that moat around the volcano.
Is it the corona that is a load?
Yes, it's the corona that's the load. And the question was whether the Earth's compositional layers, you asked about composition, whether the Earth's compositional layers change over time. So if we make a measurement today, is it representative of a couple of hundred years ago? And the answer is yes, they do change over time, but very, very slowly. And the most important structures in the Earth in terms of compositional variations were set in very early in Earth's history, when the Earth, shortly after the Earth formed, and heavy stuff, metal, essentially sank to the center of the Earth, and the lighter stuff floated to the top. The crust on the Earth does change constantly because we make, through plate tectonics, we make new crust. But those average sorts of measurements don't change. Okay, so the question was about Venus and the piece of the talk that I skipped over about Mars. So the gentleman asked why Venus does not have a magnetic field and why Mars shows some evidence for a magnetic field. And so the first answer is that, the first part to that question is that neither planet has a magnetic field that is due to the movement of liquid iron in the core of that planet today. Both planets have cores that are at least partly liquid, and we know that from some quite sophisticated measurements of the planet's wobble. So we do know that those planets have liquid cores. So it's not that they're, or at least partly liquid cores, so it's not that there isn't a liquid part to the core there. It's that somehow the energy is not available to drive the motion, sufficiently vigorous motions in that liquid core to generate a magnetic field. In the case of both planets, we think it's because they cool sufficiently slowly compared with the Earth that there's not enough heat being lost. The Mars, in contrast to Venus, and for a not obvious reason up front, does have evidence for a magnetic field in its past. So it has these very weak magnetic fields. This is the lower figure here, and that shows the magnetic field measured at spacecraft altitude on Mars. This is a better comparison. The top figure here would be the field, the magnetic field due to the Earth's crust, magnetized rocks in the Earth's crust, if you just could switch off the field in the Earth's core today. So we have to make models to, this is a model, it's not exactly how it would look, but it's about how we think the Earth's magnetic field would look at 400 kilometers above the surface of the Earth. So this is just a few percent of the total strength of the Earth's magnetic field. The lower figure shows the magnetic field strength at the same altitude on Mars, and the important thing is that the scale bar is 10 times the scale bar for the Earth, so it has really strong anomalies and some places in its crust. And so we think those places are places that are quite old, and they're places that have not subsequently been hit by large impacts on Mars or being reheated. So it preserves the record of a very early magnetic field that has, but it also tells us something about the modification of that surface. We can't even say the same thing about Venus, because Venus has a surface temperature that's so high that if the rocks were magnetized at some point in its past, over time they would have lost their magnetization. So the question was actually, you meant the lithosphere thickness on those two planets, that we think that that is thicker than on the Earth, and I used that today, and I used that as an argument for less efficient cooling and less ability of those planets to support a magnetic field. And your question was about, I think that what you were asking was that may be a valid comparison for Venus, which is a similar size to the Earth. Perhaps you would buy that, but you were speculating as to whether that may not be a valid comparison for Mars compared with Venus or the Earth because of Mars's smaller size. So we might have expected it to cool faster. In fact, smaller planets don't cool faster. They have a lower temperature at almost all times during their evolution than a larger body. So it's a really common misconception in planetary science, one that I had until recently too. But so the argument is that the comparison is valid. Smaller planets have less heat producing elements, so they produce less heat too over time.